Hello, welcome to our next set of stats notes. We are continuing on with chapter 9. We're going to still be working with two populations. The big difference here now, though, is we're going to be working with means. So the previous section we're working with proportions. Now we're working with means. So we're going to be looking at the averages, not the percentage. We're still going to be doing both hypothesis tests and confidence intervals, deal with two different populations. So in this section, we're going to do those hypothesis tests, confidence intervals, of the difference between two population means, so the average for two different populations. We'll have two different approaches, whether or not we can assume the population standard deviations are equal. So there's going to be two different approaches. It's all based on, can we assume that the population standard deviations are equal? We're going to do the not equal case first, and then we'll do the equal case later. So there are two different things. When it comes to the actual practice of this, you'll see it's basically just like checking one little box in the calculator, so it's not going to make a big difference. You have to kind of hopefully notice why we do that. We'll talk about that a little bit. Just like always, if we're doing a hypothesis test, we will need the test statistic. So if you're working with two populations that are independent, so there's no natural pairing, no connections, like in the previous section, we'll use subscripts, the N1, N2, sample 1, sample 2, that kind of stuff. And then this will be our population, or formula for our test statistic. So this will be a t-score. We are going to assume that we don't know standard deviation, so sigma is unknown, so we're still working with t-scores. We've seen this in the past, that means are always t-scores, the proportions tend to be z-scores. Just like before, the null hypothesis will be that the means are equal, and then the alternative would be that they would be not equal to, or less than, or greater than. So when we do this formula here, which it's not going to be that super important, we're not going to use it, but if you were using it, you would just basically assume that this value is 0, because we'd assume that the means are equal, and so you'd really just use this for the formula for the test statistic. So that'd be your test statistic formula. We're not going to bother really using it because technology will do this for us, but if you did need to use it, this would be what you use. And to do this, you would have to get the sample means. That's supposed to just be sample mean. I think I actually have a double equals there, but it's supposed to just be regular x bar. You have the sample means, the sample standard deviations squared, which make them actually variances, and the sample sizes, and you use all that to get the test statistic. And so you can do it by hand. I'm just never going to make you. You're going to be able to always do this with the calculator, so we're not going to really worry too much. The one thing that gets really complicated with this one is the degrees of freedom. So to find the degrees of freedom, we're actually going to pool data from both sets. So the degrees of freedom is actually done using this formula, where A is the sample standard deviation of the first group squared divided by the sample size, and B is the sample standard deviation of the second group squared divided by the sample size, and then you have to do all that. Now this would be the formula you would use if you're trying to be really precise and exact, or if you use a calculator, this is what the calculator uses. But most of the time, if anybody ever has to do this by hand, they don't want to use this formula because it's a mess. So if you're doing this by hand, what you usually do is just use the smaller of the two degrees of freedom for the two different samples. So remember, degrees of freedom, you always just take one away from the sample size, and that's the degrees of freedom. So in practice, if someone's doing this by hand, they're not trying to be super precise, because if they want to be precise, they'll use a calculator or some other technology. Then they would just kind of guesstimate, and they just use whichever sample size is smaller, and that would be the smaller degrees of freedom when you subtract 1. So that's what you do by hand. This is for like the calculator to do. So we'll let the calculator do this for us. We're not going to worry about trying to punch all those numbers in. So let's go ahead and do one. We'll find a hypothesis test for this, and you can kind of see how this works. Now, like I said, we are having two approaches. The one where we said we can assume the sigmas are, we can't assume the sigmas are equal, and that's the first one. This is called a non-pooled t-test. So in the previous section, we assume the population means are equal. So we said that, the null is that the populations are equal. The alternative that they're different, less than, greater than, or not equal to. And then we use the p-value critical approach. We're really just going to use the p-value approach to use p-value because it can be completed with technology. But when we do this, we're going to do a non-pooled test. So we're doing non-pooled. So this is like degrees of freedom. All this stuff is for non-pooled. What makes it non-pooled is we say we can't assume the standard deviations are equal. So we can't assume the standard deviations match. So what does this mean? Well, if you're doing a study and you just pick two random groups, one from like the state of South Dakota, one from the state of New York, so you have two different populations, and there's no reason to assume that the spreads from these two samples of these two populations would be similar. So maybe you're looking at like income levels from South Dakota and New York, and there's no reason to assume that those would have the same standard deviation or spread. Versus you might have a situation where you do assume groups have the same spread. If you looked at like two groups from South Dakota, you just pick the two groups at random separately. So they're two separate groups. So then maybe they would have the same spread. So the way you design your study is going to kind of determine whether or not you can assume they have the same amount of spread in the data. And so this first case is where we have two sets of data. There's no relation to make us assume that the spread matches. And so then what we're going to do is we're call a non-pooled, so it's non-pooled t-test to check and see if the populations match. So they're going to give us the sample mean for population 1, the sample standard deviation for population 1, and the sample size, the sample mean for population 2, the standard deviation for sample 2, and the sample size for sample 2. You tell us what kind of test. So are we doing a less than, greater than, or not equal to? And this one's a two-tailed test. So it's a not equal to test, and they give us the significance level because they'll tell us what significance level we use. To do this, we're going to do a two-samp because we're doing, we have two different sample means that we're working with. And we're going to do a t-test. When you're doing these, you are never going to do z-test. We would only do z-test if you knew what the standard deviations is for the whole population. That's information that you almost never have, so that's just not done very often. So we're going to never use, not for any situation will we ever use, two-samp z-test. They're both options on the calculator, right? There is a two-samp t-test and a two-samp z-test. We will never be using the two-samp z-test. We're always going to do problems where we have to use the t-test because we don't know sigma. So we don't know sigma. And we never do for means. Basically you can kind of assume with means that we have to work with t-scores. So remember, sigma is the standard deviation for the entire population. And we don't know the standard deviation for either population. We don't know that, so that's why we're always using two-samp t-test. Okay, so we're going to go to our calculator, hit that stats, go to tests, and we go down just to option number 4, and that is the two-samp t-test. You can see how it's so easy to get z instead of t. You want the t-test, and then we're going to put in the stats, not the data. The data is only if you actually have like all the data, they gave you all the inputs. So we're going to do that. X1, so our sample mean for the first population is 12. Standard deviation is 2. Sample size is 20, so just putting that in there. Standard mean for the second group is 18. Standard deviation is 7. And sample size is 20. They don't have to be the same sample size, but in this case they are. It's just, for this case. Since it's a two-tailed test, we are doing not equal to. So that's what a two-tailed test means. And then here they'll ask us, is it pooled or not pooled? In this case, it is not pooled. That's because right here it says no. So here we'd be doing a not equal to U2, and the non-pooled, so the pooled is a no. And then of course we put in all this information they gave us. Okay, so running that, we hit calculate. So it puts that all in there, and it gives us our information. So we can see that it gives us the t-score. This is the test statistic for this. So the results, it gives us your t-score, which is negative 3.68, 6 if you run that. That's a really far t-score. This is pretty extreme. So again, the test statistic, that's from your sample data, and it tells you how unlikely you are to reject the null. The more extreme this is, the more likely you are to reject the null. And also is why the p-value is so small. So the p-value here is 0.00129 if you run that, which that's like, you move this decimal 2 spots, you get 0.1%. It's really small. It's not even 1%, it's 0.1%. This also does give you the degrees of freedom. So if for some reason you know the degrees of freedom, this did all those calculations, figured it out. Again, they had to do all that stuff here. That's how they had to find the degrees of freedom. Do all this, which includes these two. Again, thankfully we don't have to do that by hand. So that's why we appreciate them doing that for us. See, I get 22.08. And then the data that you put in is there, so you can make sure you typed it in correctly. You know, the 12, the 18, the the 2, the 7, 20, 20. So all that's in there, so we can see if we did that right. Okay, so based on this, if we're going to do a p-value test, remember you take the p-value, so we take that 0.00129, and we compare it with the significance level. So we compare p-value with the significance level, or alpha, which in this case is 0.05. Well, 0.05 is much bigger, right? The p-value is much smaller than 0.05. So remember, if your p-value is low, the null must go. So this actually lets us reject the null. In this case, we're actually rejecting equality. We're saying that the averages for these two populations don't match up. We're not saying that which one's bigger or smaller because we did a two-tailed test, so we're just showing that they're not equal. So we have evidence to show that the mean 1 is not equal to mean 2. So that's what we're supporting, because that would be the alternative for this one. So when it comes to these problems, you need to figure out, since it's a mean, because we're working with sample means, that's why we're doing the two-sample t-test. This is for sample means. You need to make sure you're doing the right kind of test. It's not equal to, because it's two-tailed, and it's non-pooled. So you have to specify whether it's pooled or non-pooled. In real life, that would come from the situation, but on the homework, most of the time, they're just going to tell you. So based on what kind of study they're going to do, they're going to say, oh, well, we can see for this study that there's no reason to assume they're pooled, so we don't pool them, and so they'll just tell you non-pooled. But in real life, a statistician would have to sit there and figure out, okay, do I pool or not pool? So that's the hypothesis test for these. We use the two-SAM t-test. We can also do confidence intervals. So let's go do a confidence interval. Just like the mean, I'm going to give you the equations, but we're not really going to use these, because thankfully the calculator does the heavy lifting for us. It does a lot of the work for us. So if you had to do this by hand, you would use this formula to find your margin of error, which involves t-scores and all this stuff. And you would have to find degrees of freedom, because you're trying to use t-scores, and you would have that big degrees of freedom. Again, we're not really going to use that. Also, when we're working with two populations, remember that when we do this, we're always looking at the difference between the two sample means. That's our point estimate, and then we'd subtract the margin of error from that. So we expect kind of this to be close to 0, because we're usually looking at if these are equal. But again, the more different they are, the less likely we'll say that they actually are equal. And we can use confidence intervals again to try and determine whether or not to reject like a hypothesis test, and we, like before, we'll look to see if 0 falls inside the confidence interval, because that's how we decide. Remember that we reject the null when 0 is not inside the confidence interval. So we say that the population means are not the same. So this would be our confidence interval. This is how we get it. This is our margin of error, this formula, and then this would be our degrees of freedom, all that to get our degrees of freedom. So again, all that's work we're not going to really have to do, because we're just going to let the calculator do that for us. Thankfully, that's one thing we'll see a lot in this unit. They'll give us the information. They'll mention that it's non-pooled. I'll watch for that. They'll tell us the confidence level, so we know what kind of confidence level we have. Give us the information down here, the sample means and sample standard deviations. And this is the same set of data, just so we don't have to retype it all in. So we're going to do a confidence interval. To do the test, we're going to do a 2-SAMP T interval. And of course, the difference here is we're not doing a hypothesis test, we're doing a confidence interval. So that's why it's interval, not test, because we're doing a confidence interval. And again, we're never going to do the Z one. So we're never going to use 2-SAMP Z interval, because again, that's for a situation we'll never really see. We won't see this, Z intervals. So if we're doing means, it's always going to be T. Okay, so let's go to calculator, go to stats, tests. We want 2-SAMP T interval. So it's the interval now, not the test, because now we're building a confidence interval. So they actually say up here, get the confidence interval. That's why we're doing the interval, not the hypothesis test. Stats, same stats, right? So 12, 2, 20, 18, 7, 20. Confidence level, this time we want a 95%, so let's put 0.95, that's 95%. It is still non-pooled. We're saying that the sample standard deviations no reason to think they're matching, and we calculate. And this is what it gives us. So it gives us the confidence interval, so negative 9.375 to negative 2.625. That's the confidence interval we got from that. It does give you the degrees of freedom, which they will be the same because it's the same formula for degrees of freedom. That's what we said in the last one. And then all the stats on there just to make sure you can type it in right. So we look at that and say, okay, this is the confidence interval. This is for the difference between the two populations. This is our confidence interval, somewhere between a 9 difference to a 2 difference. And what this means for us when it comes to the hypothesis test is, note, it does not contain 0. And if it doesn't contain 0, because these are both negative, so 0 would be like over here, it does not contain 0, then we reject the hypothesis. So, reject the null hypothesis. And so we say that the populations, the population means aren't equal. So that's what this would be doing. So since it's a two-tailed test, this would be like a 5% significance level test if we did this. Because you always look at this, 95% would be the middle, and so you have 5% of the two tails. So it would be like doing this test at 5% level, we would say, reject the null, they're not the same. So if you're doing the hypothesis, if you want to try and use the confidence interval, do a hypothesis test, and you're always looking to see if it contains 0. If it doesn't contain 0, then you can say, nope, that's not 0, doesn't make sense, it's not part of what I got in my interval, and so I reject that equality statement. So you should be ready to do the 2SAMP-T test and the 2SAMP-T interval. Both of these ones were non-pooled. Again, that means that we're not saying that the two have the same standard deviations, and so we just use the non-pooled option. The other thing we're going to do for you is when we actually have the standard deviations assumed equal, in this case we'll just do pooled. That's because we're assuming the standard deviations for the two groups are equal. So the two groups we picked probably came from the same main group or something like that. So sometimes you might make sense to assume the standard deviations match. You'd still use the test statistics calculation. Again, this would still be 0. But now when you do this, you're actually using the pooled standard deviation here. And that's what this is. So this pooled standard deviation right here, this is actually the variance because it's squared, is what they're putting in here. So if you're doing the formula by hand, you have to use this whole formula to do this formula. But again, we're not going to do this by hand, so don't freak out too much because none of it we're actually going to use. We're going to let the calculator do all that for us. Isn't it amazing that we have a calculator that just makes our life so much easier? Because you could just type all these numbers in, and it just gives you an answer. It's a decimal and all that. But it's so much easier just to put in the data and note that they'll tell us this time to do it pooled. So we just put in there pooled, yes. And that's the big difference for us. It's still a left-tailed test. This one is going to be significance of 0.05. That is different numbers, so I'll have to put in different numbers this time. But it's still going to be 2SAMP t-test. So we're going to do a 2SAMP t-test. So it doesn't matter whether it's pooled or non-pooled, you're still using the same test, the 2SAMP t-test. Again, we're not using z's. The only difference is you're just marking it as pooled, not non-pooled. So go stats, tests, 2SAMP t-test. Put in, the data they gave us, so 16 for the sample mean, 6 for the standard deviation, 23 for the sample size, 19 for the other sample mean, 5 for the sample standard deviation, and 18 for the other sample size. Because it's, left-tailed. This one's left-tailed, so this is a less than, because it's left-tailed. We're going to do a less than, because it's left-tailed. And this time it's pooled, so this is a yes, it is pooled. Put in yes. So if you put no one said yes, or if you put the wrong tail, it can give you the wrong answer at the end. So you want to make sure you always have the right type of tail here, and you have the whether it's pooled or not pooled. If you don't have a pooled option, you use the wrong test. That's something you can always tell. If it says pooled and you don't ever get the option for pooled, then you use the wrong test. Got all that in there, hit calculate, and this is what it tells us. So this is the test statistic, make it 1.7065. The p-value is going to be 0.0479. It gives us the degrees of freedom, but this one's actually 39, pretty high degrees of freedom for that one. there you go. So that's our information from there. So then, and then it actually does give you the pooled sample standard deviation. So that little SP, that we had up here, there's that pooled sample standard deviation. This one you'd have to square to get that because this is the variance. But it gets to that information, so it's cool that they get that. I get that. So if you need the SP, it does give it to you. It's the 5.586. But for us, really all we need to do the hypothesis test is the p-value, because we always just compare the p-value with the alpha or the significance level. So we're just compare the p-value of 0.0479 with the alpha 0.05 and say that it is less, right? 0.0479 is less than 0.05, and so we reject the null. Again, we have extreme enough evidence we can show that because this sample mean is so different from that sample mean, you can say that they're far enough different that they're not equal. The populations don't match up. That's what this shows us. So we reject the null, so we can say that the mean one, in this case, we actually show that mean one is less than mean two, because we got a small enough mean the first time versus the second time. We can say, yeah, it actually is smaller. That's what we're supporting the alternative, is that the first one's smaller than the second. So that's the idea. Pooled, the only difference is marking that pooled box. So you can see it's not a big difference. It doesn't really matter too much except for each one. Make sure whether you mark whether it's pooled or not pooled. We'll do a confidence interval for this, and then we're pretty much done. That's all there is for this section. The big thing is identifying when you're doing this. I think when it comes to Unit 3 exam, that's sometimes the hard thing, is noticing which problems go with which formula. Notice here we have two different populations, and we're looking at means, and that's kind of a big hit. Again, they're going to give us the formulas for the margin of error, the formula for the sample, pooled sample. Degrees of freedom for this one is actually n1 plus n2 minus 2 for the pooled version. That's some kind of crud on my paper, sorry. But again, if you're not doing this by hand, the calculator really gives you all that information. So we're really just going to run a 2-samp t interval. We're doing interval because we're looking at a confidence interval. We're not doing a hypothesis test, we're trying to do a confidence interval. You can use it to do a hypothesis test, but we want a confidence interval, and we're doing this at the 95% level. And again, they'll give us the data. I left it the same, so we wouldn't have to change it again. Keep these notes kind of short and sweet. So let's go to stats, tests, 2-samp. I went to the bottom, so I have to go up to 2-samp t interval. So again, t interval, we're not going to use the interval. 2-samp t interval. This should be 16, 6, 23, 19, 5, 18. Confidence level is 95%, so I'll leave that. But this time, pooled, it is pooled. I'll make sure that that says yes. So it does say yes, so I'm good to go. And I can hit calculate. And that's my confidence interval. So the confidence interval for this one, I think 6.556 over to 0.5558. This one, notice that this contains 0. So it contains 0. So we would fail to reject. The reason why this one's different than the last one is because when we do a 95% confidence level, we're actually only doing, like this would be for a 2.5% significance level test. If I wanted to do this and get like the same result as the last time, I would have to take that alpha and double it. So I do like a 90% test, and then I would not see the result, because you always have to think about those confidence levels and how you have to have the two ends and how I have to the data, the percentage has to fall on both. So I do 95%, I have 2.5 on both sides, not 5% on both sides. Again, you don't really need to worry too much about that, because you could just use the hypothesis test. If you know the significance level, just use the hypothesis test to test it. Really only worry about doing a confidence interval if you're trying to find the confidence interval. No reason to do this method for checking. It's something you can do if you want to. You can check your hypothesis this way. But again, this is for actually a 2.5% significance level for one-tailed test. So that's why I got a different result this time, because this is technically like a 2.5% significance level if you're doing a one-tailed test. Okay, so this section, It's all about means. It's all about two populations, and they give us the means, and finding the confidence interval or finding the hypothesis test result, whether or not to reject. Again, you're always looking at quality as the null, and so when you reject that, you're going to have the opposite, the less than, greater than, or not equal to. And the big thing here is that these are means, not proportions. Since they're means, that's why we're working with t-scores doing means. That's why we're doing the 2-SAMP t-test or 2-SAMP t interval. That's it for 9.2. 9.3, we'll finally look at what happens if the two sets of data, the two populations, are linked. Because so far we've been dealing with data where the two sets are not linked in any way. There's no natural connection. So 9.3, we'll look at what happens when there is a natural connection. So I'll see you on the next step.